and exponentials is going to be the section. Well, I'm sorry, logs, exponentials, and recursive formulas. You should have done logs and exponentials. You do exponentials as early as Math 1. And you should have done logs in Math 3. I think it's Math 3. So those should be familiar. I think recursive formulas are going to be new to you, but they're kind of fun. Usually students last year kind of liked them. So I think we'll do fine with that. So let's start just going over sort of what is a logarithm. Because logarithms it's weird math, right? Adding, subtracting, multiplying, dividing, that's common knowledge, you know. Logarithm is weird math. This is when you start to be impressive whenever you bring your homework home and your parents are like, oh, I don't know how to do that. And maybe some of you have some parents that can do it, but most parents can't. You can impress them with your work. A logarithm is the power to which a number must be raised in order to get some other number. So, for example, 2 must be raised to some power to get 16. What power is that? What is that x going to be? 4. So x would be 4 in this case. 2 to the 4th power would give us 16. So the other way that we could talk about this is we would say the base 2 logarithm of 16 is 4. So log base 2 of 16 equals 4. That's the other way we could write that in symbols. And hopefully you can all see the screen. If anybody cannot, let me know, and I can find you a different seat. Alright, so if I have something like 2 to the x power equals 1024. Right, so 2 to the x power equals 1024. Anybody know what that one is off the top of your head? 10? Okay. Alright, so the base 2 logarithm of 1024 would be, what's happening here? Okay, 10. So that would be written like this. Log base 2 of 1024 equals 10. So a logarithm is what power do I need to raise this to get this number? That's what you're thinking of here. This is printed out for you. You don't have to write anything down here. But so just a few things that use logarithms in real life that I want to introduce you to. There's the Richter scale, which whenever we talk about earthquakes, I at least always hear them talk about the Richter scale. The Richter scale is actually outdated, I learned whenever I was looking at this a little bit. And we don't actually use the Richter scale anymore. Like whenever you hear that the earthquake in Haiti was a 7.2, in modern science they're using the moment magnitude scale, which people still a lot of times will refer to as the Richter scale, but it is actually different than the actual Richter scale. So I found that interesting. But they're both based on logarithms and they're similar. They just changed it some for to make it more standard, I think, whenever they did the moment magnitude scale. You have the decibel scale, that's for sound intensity, and we'll look at an example of both of those. Data analysis is something where you're going to use this a lot, or see this a lot. It's especially helpful if you're looking at things that have really, really large numbers, because logarithms sort of help take care of dealing with those. Some other instances, could be, well, like I said, anything where you have to deal with really, really large numbers. That's going to be used. So, show you a couple examples. Here's an example of the Richter scale. I just pulled one here. What you have to remember about logarithmic scales is whenever you're talking about logarithms, you're talking about, like, let's say if this is log base 10, we're thinking 10 to what number, to what power gives us this number. So each step on the Richter scale is actually 10 times stronger, right? So when you go from a 3 to a 4, it's not just like one bigger, it's 10 times bigger. So if you go from a 4 to a 5, again, it's not one time bigger, it's 10 times bigger, which means that if you go from 3 to 5, you've multiplied by 10 twice, which means it's 100 times more intense. So that's why the earthquake in Sparta we had last year, what was it? It might have been 5, maybe. Sorry. I'm not used to talking all day with this mask on. I think it's getting me a little tickle in my throat. The earthquake in Sparta was like a 5 maybe, and you could feel it here, and it broke. Some weak buildings were hurt there, but a 7, of course it was in Haiti where the buildings are not quite as strong, but a 7 can be devastating, right? Because a 7 is 100 times worse than a 5. So if you can imagine, do you guys remember that earthquake last year that was in Sparta? Did you guys feel it? We were actually like in Asheville, and I could even feel it whenever I was there, but just barely. So if you can think of what that was, if you could make it 100 times worse, that would be a 7 on the Richter scale. So much worse. So you can go from, 3s are, 1 through 3s are generally not even felt. Once you get past the 3, this is going to be minor, but when you get up here, it's going to be a lot bigger. Noise levels are the same. So like if you go from a 30 to a 40, it's 10 times bigger. I don't love this chart because it doesn't go up 30, 40, 50, 60, 70. It skips some numbers, right? So like going from 40 to 50 and 40 to 60, because there's a 50 right here, that's actually 100 times louder, right? So whenever you're looking at that, so whenever you get up here above 85, noises can be harmful, especially for a long time. So like you go from like a 90 to this is a 101. You got subway to school dance is not good for your ears for a long time. So those are sort of examples of where this applies. So this is sort of interesting. Another thing, I forgot to put this one in here, or maybe I did. Let me check. Got it. One thing I look at, I don't know how accurate this one is. I use it a lot, but I like it because of the graph. This is one of the places I look at coronavirus numbers sometimes, and I like it because it gives good graphs. So like if we pick the U.S., here's the graph of the total cases. So this is going up. You can notice the Y scale here. You got 10 million, 20 million, 30 million, 40 million, 50 million. This is normally how we scale something, right? We just go up by 10 million here. But if you have a logarithmic scale, you're multiplying by 100 each time instead of adding 100. So this does not give you good information about what was happening at the beginning, right? Because the numbers are so tiny compared to what they are now that you don't really see it. So logarithmic kind of gives you an idea of what was happening here at the beginning. Maybe it's slightly less helpful now, right? Because we're not seeing as much exponential increase. But you go 1, 100, 10,000, 1 million, 100 million. So when you're dealing with really large numbers of things or exponential growth, sometimes it's helpful to look at a logarithmic graph with that logarithmic scale there. So, all right, let's work on doing a few things with logarithms. So what we need to remember is how to rewrite these, go from exponential to logarithms and logarithms to exponentials. Logarithms and exponentials are inverses of each other. Yeah, So they undo each other. So if I have b to the, let's see which letters, a power equals x, we would call this b right here, that is the base of that exponent. It's also going to be the base of the logarithm whenever you rewrite it. So log base b of x would equal a. So this is sort of the formula you're going to use to translate. So if you don't, I would probably write this down. So your base raised to a power equals x. That base has to be the base of the logarithm. And I always tell students, you need, whenever you rewrite an exponential as a logarithm, you're trying to break up whatever was together. So b and a were together here. So b has to be the ace. A cannot go with it. A has to go here on the other side. So these two have to switch places. So for this first example, if we want to rewrite this as a log, we would say log base 5 of 25 equals 5. And so I'm going to get some of you guys to help me here. I'll take volunteers right now. Who could tell me what to do for number 2? Yes. Uh-huh. Yes. Thank you. Yes. So, since you're correcting me, what would you do on number 2? Perfect. Good. And you can put some parentheses here or not. A lot of times if I'm handwriting, I do like to put the parentheses because it just helps keep it. A lot of times you'll see it without the parentheses if it's tight. All right. So who can help me with number 3? Somebody else. I only get harder from here. I'd grab an easy one right now. All right. Zach. Not 3 on this one. Because our exponent here is an x. You might have been looking at the one before. Okay, questions? Alright, let's do this in the opposite order. So this is our base. Over here, this is going to be our exponent. So we'll have 5 to the 4th power equals 625. Who wants to try number 5? All right, Major?
2 to the 30 is 8.
Perfect. All right. How about number 6? Who wants to try number 6? All right. Let me think for a second. I can't get it. What's your name? Cade. Okay, Cade. What is it?
7 to the power of 10.
Perfect. Okay, any questions? You guys have done this before? You remember seeing it? Even if you didn't remember how to do it exactly, it's at least familiar. All right. Okay, there are 2 special logarithms that we have to know about. If you ever see a logarithm without a base, that is what we call the common log, and it is automatically a log base 10. So if no base is written, it's automatically a 10. If you have a log, if you have a ln, this is what we call the natural log, and it is a base e. E is a little bit like pi, and I don't have it written down here. E is 2.141. No, that's pi. Hold on, 70. 2. I'm gonna have to use my calculator. I know what E is. 718, that sounds right. And it goes on longer than that, 2.718. Okay, it keeps on going. So it's like pi, it's a set number. We'll talk a little bit more later about what that is and why we use it. But those two are the special logarithms that we have to know, and we're going to see a lot. In fact, whenever you get to calculus, you pretty much only use natural logs most of the time. We don't do a lot of the other logs whenever we get there. So, what's important for us to remember is that logarithms and exponential functions are inverses of each other. Okay? So, whenever you think of adding, the opposite of that would be subtracting, right? So, if you add 3, and you undo that, you could subtract 3, right? Inverses of each other. Same thing with multiplication and division. If you multiply by 4, and you need to undo it, you would divide by 4, right? So, if you have a logarithm, the inverse of that is an exponential. If I have something like this, if I have log base 3 of x equals 4, something like this, you can just rewrite it. So one way that you could solve that is you could say, oh, there's my base, 3 to the 4th power equals x. So I just got to do 3 to the 4th power, which is 81, is my x. Or you can think of it this way, and I like to do this whenever we're doing the more difficult problems. The opposite of a log, the inverse of a log, is an exponential. So if I do 3 to this power right here, it cancels out that logarithm, and I'm just left with x. Then I got to do 3 to the power on this side. So x equals 3 to the 4th, which gets me to the same answer over here. Two different ways of thinking about really the same problem, right? For domain, and we'll talk about this more when we get to section 1.4, but you cannot take the log of any number less than or equal to 0. Let's talk about why that is. And let me check time. When do we get out of here? Third period. You guys have lunch at 1:10. Okay. Well, we're good. Okay. So we would have, for example, let's say that we have log base 4 of -3 equals x right here, right? You can type it into your calculator. If you do, you're going to get that it is invalid, right? It's not going to work. But let's think about why this is. If I rewrite this, it's 4 to the x power equals -3. So think to yourself, what could you raise 4 to that would make it -3? If you do 4 to the -1, remember, what do we have to do with negative exponents? We move that, well, you're not moving the decimal. You're going to move the decimal if it's like scientific notation. You'll move the decimal. But in this case, it's going to go to the bottom of the fraction and become positive, right? So 4 to the -1 is really 1/4, right? And if I had 4 to the -2, I'd get 1/4 squared, which would be 1/16. Right? And I could keep doing that with negative numbers. Am I ever going to get a negative answer? No. Because they're just going to, I'm going to have like tinier and tinier and tinier fractions, but I'm never going to get a negative, right? And so it is never even going to get to 0. Although it'll be really close, like 1/4 to the 100th power is going to be really close to 0. It's not going to be 0. So this is why you cannot take the log of 0 or a negative number. What this means for us today while we're solving equations is we need to plug answers back in to make sure we are not taking a log of 0 or a negative number. And we'll see that here in a minute when we start doing some example problems. We want to make sure that we're not trying to take log of a negative number. Okay. One more thing I want to show you before we go on to do some problems is the change of base formula. If you prefer using your TI-84 calculator and you don't have like the newest version of it, you got to know how to do this because it's not going to do logs very easily without it. If you like Desmos best, then you don't necessarily have to know how to do it, but this is something that maybe sometimes might show up on like ACT stuff, so you still might want to know it. All right. So the change of base formula is just that if you have log base A of B, that is equivalent to log B over log A. So, in the calculator, let's see if this works for me today. And I actually just prefer to do this either way. It's just easier to type in log. Like, for example, let's say that we're doing log base 4 of 12. I could just type that in as log 12 divided by log 4. Or I could type in natural log of 12 over natural log of 4. It doesn't matter if you use common log or natural log there. So I could just type in log of 12, make sure you close that parentheses, over log of 4. And I get 1.729 just to prove that it does actually work. If I do natural log instead, it doesn't make a difference. I get that same number, right? So 1.792. Yeah, 792. Just a quick side note. For rounding for me, unless I tell you otherwise, round to 3 decimal places for me. On the AP Calculus exam, all answers must be accurate to 3 decimal places. You can keep more decimals if you like. So if you want to write down that whole number, 1.79248.125, that's fine. Do that. I'll take more decimals, but don't give me any less than 3, unless I've told you otherwise. Okay, that's generally my policy for everything in this class. Okay, all right. If you use Desmos, because Desmos is great and I love it. If you had Mr. Brown, I don't know that he loves it as much as I do. If you had Coach Wood, he probably loves it more than I do. In Desmos, you can still do this. I like using change of base formula, just because it's just easy to type in. But Desmos will do bases here, so if you go to functions, miscellaneous log here, so you could type in log base 4 of 12, and you can see you get that same number. So either one is fine for me. There's a good chance you're going to have a calculator there might be parts of your test you are not allowed to use Desmos on, just because if I give you Desmos, I got to give you your phone or the computer. So you need to know how to do it in the calculator also. All right, so let's do some problems. Oops. All right. Okay, so as I showed you earlier, you can either rewrite these or you can use inverses. I'm going to work on using inverses just because I kind of like to. Okay, I think it helps us for our understanding later on. So 5 to the x, the opposite of 5 to a power is log base 5. So what I'm going to do is I'm going to take log base 5 of both sides of this equation. And log base 5 and 5 are going to cancel each other out, just leaving me with this little x right here. Now on the other side, I've got log base 5 of 9. Or rewrite it. Log base 5 of 9 equals x is what you're going to get if you do that. And so we can just simply type this into the calculator. Natural log of 9 divided by natural log of 5. And we get 1.365. Okay, questions? All right, on this next one, we got a base of 8. So I'm going to do log base 8 on both sides here. And so log base 8 and 8 are going to cancel each other out, and I just have the x. And it's going to equal log base 8 of 450. So log of 450 over log of 8 is going to be 2.938. Okay, questions? All right, 3 becomes a little bit trickier because instead of just having an x, we've got 2x minus 4. But we're still going to do the same thing. That 10 is the furthest away from the x. That's what we need to get rid of first. So we're going to do a log base 10. But remember, a log base 10 is just that common log. We don't have to put log base 10 there if we want. You could write it if you want. It's technically correct. It just is unnecessary. So we're going to do this. So we'll get 2x minus 4 equals log of 800. And then log of 800 we can just type into the calculator. We're at 2.903. Keep this whole number in your calculator as you're doing this problem because you don't want to round the answer off until you get to the very end. So we got 2x minus 4 equals 2.90308. All right, so now we're down to a simple equation. So Wesley, what will we do next to solve this equation? Perfect. So we'll divide by 2 there. And so x will equal, so I'm going to add my 4, divide by 2, and I get 3.452 if I round that off. Okay, questions? Yes.
Why don't you divide first? Why do you add 2 instead of 9 2?
You need to be working like the opposite of order of operations pretty much. So whatever you would do first, if like you had that x, you're doing the opposite. So I always sort of tell students that 4 is further away since it's separated by that negative, so you want to get rid of it first. And then you will divide by 2. So generally whatever's multiplied by that x, you're going to do that very last. Okay, let's look at 4 because it's a little bit different. We've got 10 minus e to the x equals negative 9. Now, this time, On all of these other ones, we just had a number raised to some sort of power, right? Even on this one, there's still 10 and everything was in my exponent, right? But on example 4, that's not the case. I've got this 10 over here, and that 10 is separate from my e to the x. So when I'm solving this, I want to get rid of that 10 first. So I'm going to subtract the 10. And so I've got negative e to the x equals negative 19. I've also got this negative right here that's outside of the exponent, right? So what do I need to do to get rid of that negative? Divide by that negative 1. It's going to make both sides positive. E to the x equals positive 19. And so now the opposite of an exponential is a logarithm. So, and in this case, it's going to be log base e, but what's the special name we call log base e? It's natural log. So I'm going to take natural log of both sides. Natural log cancels out the e, and you've just got an x right here equals natural log of 19. So if we type that in, we're going to get 2.944. Okay, questions? All right, so all of those problems were exponential problems, and we used logarithms to solve them. Now let's look at the opposite. Let's look at a logarithm that we're going to use exponentials to solve. Okay? So I've got, for example 5, I've got log of x equals 90. And Sarita, whenever I look at this, I don't see a base of that log, so what is the base? What number is going to be our base if we don't have anything written there? 10. Good. So we have an imaginary 10 there, even though it's not written. So if we want to undo a log base 10, we're going to do 10 to that power on both sides. So that 10 and the log base 10 cancel each other out, just leaving you the x. And x is going to equal 10 to the 90th power. I'm going to leave that answer 10 to the 90th power because that is a 1 with 90 zeros, so I'm not going to write that out. Let's just leave it there. If you get it, yes, it is 1e90. And we don't want to have to mess with that. So let's just leave it 10 to the 90th there. If I generally try to avoid giving you numbers quite this large, although in context, sometimes you need this if you're dealing with really, really, really large numbers. But on just like homework, I try to avoid those. But if you get something, let's say bigger than 10 for your exponent, just leave it with exponents. That'll be fine. Okay. All right. Questions? Yes.
When it's log x, is it always like 10? Like, is it always like the exponent?
Yes. So if you ever see, like, for example, like if I had, even if I had like log of x plus 4, something like that, if there is no number here, that's always a 10. All right. Okay. All right, so for number 6, everything's inside of this logarithm. My base is 5 this time, so I'm going to do 5 to that power on both sides of the equation. And this is going to cancel out over here, so I'm going to get x minus 4 equals 5 to the, I'll tell you what, let's do this. Let's just do this. Let's just get rid of that 0 right there, and let's pretend like it's 2, because that's really just not the best question. I should have fixed that on these notes. Let's pretend like it was just 2 and not 20. So if I've got 5 to the second, that's just going to be 25. So x minus 4 equals 25. And let's see. Elijah, what would I do to finish solving that? Perfect. So x would equal 29. Okay, questions? All right, we got a couple more. For number 7 here, I've got 2 natural log of x plus 3 equals 7. Now, in this case, there's no parentheses, so the only thing that's with our natural log is just that x, right? So before we can do exponents to get rid of our natural log, we've got to get rid of this 2 and this 3. So, let's see. Matthew Bashirs, what should we do first? We've got to get rid of the 2 or the 3 first. Which one should we mess with first? No. Let's get rid of that 3. How would we get... Yeah, we'll subtract the 3. So we're going to do that subtraction first, which is kind of the question that Matthew Pelkey asked earlier. You generally need to get rid of that addition or subtraction before the whatever's multiplied there. So we got 2 natural log of x equals 4. All right, Paul, what would we do next? Good. When you get rid of that 2, it's multiplied, so we're going to divide by 2. So we got natural log of x equals 2. And, Raven, what is our base on the natural log? What number or less? It's the 2.718. It's that e, right? So e is our base here, even though it's not written. So anytime you have ln, e is your base, which means you want to do e to the power on both sides to get rid of that natural log. So you're going to have x equals e squared. And so to do this on your calculator, it's right above natural log. So if you do the blue button, oh wait, first turn the calculator on. Blue button and natural log, it'll do e to the power. We want to do 2 here. So we're going to get 7.389. Okay, questions on 7? All right, for our last one, Josie, what would be the base on this log? Who can help her out? What would be the base on this log? What do you think, Bo? It's 10. Because if there's nothing written, it's going to be a 10, right? If it's log and nothing's written, it's 10. If it's ln and nothing's written, it's an e. So this has a 10 right here. Well, look what's going to happen here on this problem. We want to get rid of the natural log, so we got to do 10 to this power right here and 10 to the power over here. It's going to cancel the logarithms on both sides, right? So you're just going to be left with 4x minus 3 equals 3x plus 10. So you can basically just drop those logarithms. Coach Wood likes to call this dropping the logs, and he thinks that's really funny to say. So he'll probably, like if he walks by right now, he'll probably say something about dropping the logs. So you're just left with a regular equation now. So let's see. Zach, what would you do first to solve this equation?
I'd add 3 to both sides.
Okay, we can do that. So we got 4x equals 3x plus 13. What would you do after that?
I would divide the 3 by that.
If you do that, it's only going to get rid of just your 3, and your x will still be there. It's going to be really complicated. What you want to do instead, because you're like moving this whole thing over to the other side, You just want to subtract the 3x because it's a positive 3x. So we're going to subtract that 3x, just combining those like terms. So we'll just get a 1x over here. So just x equals, and then the 13 is left over here. Now, one thing I forgot to make you guys do on these log problems is I told you on the last slide that you cannot take the log of a negative number, right? So what we should have been doing the whole time is making sure if we plug our answer back in that we're not taking a log of a negative number. So like 10 to the 90th, no problem there. That's not negative, right? So it's fine if we plug it back in. Right here, 29, I would plug it in here. 29 minus 4, that's 25. It's still positive. That's fine, right? 7.389, you're just plugging it into the x. That's positive. That's fine. Right here, you'd have to plug in 13. So 4 times 13 minus 3, I'm not quite sure what that is off the top of my head, but it's positive, so it's okay. Same thing over here, 3x plus 10. You may run into a question where you get an answer, but when you plug it in, the answer is, it's going to be negative, and you're taking the log of a negative, and if that's the case, it would be no solution for that. All right, questions? Okay, so we've got about 15 minutes. I've got an assignment for you guys, and it is going to look super long, but a lot of it at the beginning is rewriting. So hopefully you can get the whole front page done before you go. So this will be your homework tonight, which you did not get to finish. If you do not have a graphing calculator, Desmos works great on this. So you can use that instead. And I told you guys not to have your phones out because we only have 15 minutes. Those of you who do not have your own graphing calculator, I'm not going to have you guys get up and get one today. You can just use your phone for the calculator if you want today, because I don't want to go get them and just have to put them back. Plus we have to wipe them off whenever we use them. So go ahead and get started. I'm going to sort of walk around to see if you guys have any questions. I do have duty in the morning, so if you do try to come by for smart breakfast, I will not be here because I have duty. I will be down, however, I will be down there outside of the media center in that hallway where they have lunch tables set up. So if you have questions, you're welcome to bring it by there, and I can help you there because it's generally not too rowdy.